In April 2025, in an office at the University of Cambridge, a dataset arrived from a telescope floating 1.5 million kilometers from Earth. The team had already found water on K2-18b. They had found methane. They had found carbon dioxide, a planet 124 light-years away in the habitable zone of a small red star, with an atmosphere that looked, at least on paper, like it belonged to a living world. But there was one more molecule they had been hoping to see, one that on Earth is produced almost exclusively by marine life. Dimethyl sulfide, the smell of the ocean, the chemical signature of phytoplankton blooming in distant seas. The data came back, and there it was, a faint spectral line at exactly the wavelength where dimethyl sulfide should appear. 3 sigma confidence, roughly a 1 in several hundred chance it was noise. The team wrote their paper. Headlines like it ran within hours. The strongest sign yet, they said, that this small, distant planet might not be empty after all. And then the rest of the scientific community looked at the same data, and everything became much less certain. This is the story of a planet called K2-18b, a world larger than Earth, smaller than Neptune, orbiting a red dwarf in the constellation Leo. It is a planet that does not exist in our solar system. We have nothing like it to compare it to. And that is exactly why it matters. For the first time in human history, we have pointed our most powerful telescope at a planet in another star system and asked the question that has defined our species since we first looked up at the night sky. Are we alone? And the answer we got back was not yes. It was not no. It was, we are not sure what we are looking at. But here is what's also true. We have entered a new era. An era where the question of life beyond Earth is no longer philosophical. It is observational. It is being tested, debated, analyzed and reanalyzed in real time by competing teams of scientists using the same data and reaching different conclusions. By the end of 2025, at least 6 separate research groups in different countries using different tools with no coordination between them had independently rerun the same Webb data. This is not one scientist doubting another. This is the entire field checking one planet's homework. This is what science looks like at the frontier. It is messier than the textbooks suggest, and it is far more interesting. The question this video will answer is not whether K2-18b has life, because the honest answer is that we do not know. And anyone who tells you otherwise is not telling you the truth. The question is, how close are we to finding out? And what would it actually mean if the answer turned out to be yes? To understand what happened in that Cambridge office, you first need to understand what kind of world K2-18b actually is, because it is not like Earth. It is not like anything you have ever seen. K2-18b was discovered in 2015 by the Kepler Space Telescope. Its star, K2-18, is an M-dwarf, a red star smaller and cooler than the Sun, burning at about 3,200 degrees Celsius compared to the Sun's 5,500. The star is so faint you cannot see it from Earth with the naked eye. But it is there, in Leo, 124 light-years away. The planet itself is about 8.6 times the mass of Earth and 2.6 times its radius. It orbits once every 33 days, so close to its star that if you stood on its surface, 1 year would last barely more than a month, and you would be tidally locked, one hemisphere in permanent day, the other in permanent night. It sits in the habitable zone, the distance from its star where liquid water could, in principle, exist on its surface. Its equilibrium temperature is about -8 degrees Celsius. Cold, but not frozen solid cold. With the right atmosphere, with the right conditions, water could flow. In 2023, the James Webb Space Telescope turned its mirror toward K2-18b. Webb does not take pictures of exoplanets the way you might imagine. It does not resolve them into disks or see oceans and continents. Instead, it watches the planet pass in front of its star, a transit, and measures the starlight that filters through the atmosphere. Each molecule in that atmosphere absorbs light at specific wavelengths. It leaves a kind of barcode in the spectrum. Read the barcode and you read the chemistry of an alien sky. What Webb found in 2023 was remarkable. Methane, carbon dioxide, water vapor in a hydrogen-rich atmosphere. And yet, there is a problem with this picture. The presence of these molecules tells you nothing by itself about whether a planet is alive. Methane is spewed out by volcanoes. Carbon dioxide exists in the atmosphere of Venus, which is about as far from habitable as a planet can get. And water turns out to be abundant. We have found it on Mars, on comets, on the moons of Jupiter and Saturn, in interstellar clouds. Think of it this way. If you walked into a room and found a chair, a table, and a window, you would not immediately conclude someone lived there. You would have found the conditions that could support a person, but you have not seen them. You have not heard them breathing. You have found the furniture, not the resident. That was the state of K2-18b in 2023. It had the furniture. The question was whether anyone was home. In the years before Webb's observations, Niku Madhusudan and his colleagues at Cambridge had been developing a theoretical model for a new kind of planet, one that does not exist in our solar system. They called it a HY-Xi'an world, HY for hydrogen, Xi'an for ocean, a planet covered entirely by liquid water, wrapped in a thick blanket of hydrogen gas. If such planets existed, they argued, they would be ideal candidates for life. The ocean would be warm, protected from the vacuum of space by the hydrogen envelope. The chemistry would be rich. And, critically, the planets would be large enough that even Webb, stretched past what it was built to do, might detect the chemical signs of biology. Not everyone agreed. Other teams modeled the same data and reached different conclusions. Some said K2-18b was a gas-rich mini-Neptune with no surface at all, an atmosphere that just kept going until it turned liquid under pressure. Others suggested a magma world, an ocean not of water but of molten rock. The planet was the same. The data was the same. But which model you chose determined whether you saw a living world or a dead one. But Madhusudan's team was not finished. They had predicted that if K2-18b were a Hycean world, if it really had a water ocean under that hydrogen sky, then Webb might see something else, a molecule that on Earth is almost exclusively a signature of life, dimethyl sulfide, DMS. On our planet, DMS is produced by marine phytoplankton, microscopic organisms floating in the ocean, blooming, dying, releasing this molecule into the water and then the air. It is the smell of the sea. If you have ever stood on a beach and breathed in that sharp organic scent, you were breathing dimethyl sulfide. It is produced in such quantities that it plays a role in cloud formation, the sulfur compounds released by phytoplankton seed clouds over the oceans. Life, in this sense, shapes the climate of an entire world. Imagine standing on the shore of that ocean, not on Earth, but on K2-18b. The sky above you is not blue but hazy with hydrogen. The star a dull red disk near the horizon, locked in place because the planet does not turn. The water stretches in all directions, and in it, something is alive. Something is releasing the same molecule into the air that phytoplankton release into ours. And now, 124 years later, the light from that moment has struck a mirror we placed in space. This is what Madhusudan's team believed they might have seen. In April 2025, they announced that Webb had detected spectral features consistent with DMS, or a closely related molecule, dimethyl disulfide, at 3 sigma confidence. To understand what 3 sigma means, you have to understand how astronomers measure certainty. 1 sigma means the signal might be real, or it might be noise, roughly a 1 in 3 chance of being a fluke. 2 sigma, about 1 in 20. 3 sigma, roughly 1 in several hundred. That sounds strong. In everyday life, it is. If someone told you there was a 1 in several hundred chance your plane would crash, you would not board. But the standard for a discovery claim in physics is 5 sigma, not 1 in several hundred, 1 in several million. It is the difference between hearing a sound in the next room and being certain someone is there, versus hearing a sound and thinking it might have been the house settling, or the wind, or your own footsteps echoing back at you. And it was this, if anything, that put the uncertainty in the detection. Within weeks, other scientists began examining the same observations and reaching very different conclusions. Luis Wellbanks is an astronomer at Arizona State University. He did not set out to disprove anyone's claim. He did what scientists are supposed to do. He took the same data and asked a simple question. If you assumed the signal was not DMS, could you explain it with something else? The problem Wellbanks discovered is something astronomers call spectral overlap. The wavelengths where dimethyl sulfide absorbs light sit very close to the wavelengths where methane, carbon dioxide, and other hydrocarbons absorb light. So close that depending on how you process the data, how you bin the raw observations, which molecules you allow into your model, the signal attributed to DMS can appear, weaken, or vanish entirely. It is like listening to an orchestra from outside a concert hall. You can hear the cellos, the timpani come through clearly, but there is a faint high note, maybe a flute, maybe a piccolo, maybe just the wind whistling through a crack in the door. If you already believe there is a flute in the orchestra, you might convince yourself you hear it. But if you do not assume anything, the sound could be almost anything. Wellbanks showed that the apparent DMS signal could be replaced with ethylene, an unremarkable hydrocarbon found in countless places across the universe, with no loss of fit to the data. A follow-up study tested dozens of different ways of processing that same MIRI data. Only 12.5% of those methods showed any DMS signal at all. Change how you slice the data, and the signal mostly disappears. A separate team combined all of Webb's observations across its different instruments and reported insufficient evidence for either sulfur molecule. None of this proved DMS was absent. It proved that the claim it was present did not yet hold up when other people ran the numbers, which, in science, is the test any claim has to pass. But here is where it gets stranger. A separate reanalysis that year found the methane signal holding at 4 sigma. Strong, but a step down from the original claim. Carbon dioxide was murkier. One team found no trace of it at all. Another, months later, said they found it after all. And the DMS signal, it persisted at about 2.7 sigma. Weaker than before, but not gone. Still below the threshold for a discovery. Still above the threshold for being dismissed as noise. The molecule hadn't disappeared. It hadn't cleared the bar either. It was simply there, at the edge of detection, waiting for more data. This is not the first time a potential biosignature has sparked fierce debate. In 2020, a team announced the detection of phosphine in the clouds of Venus, a molecule that on Earth is associated with anaerobic life. The announcement generated headlines, press conferences, and global attention. Further analysis showed the signal was far weaker than initially claimed and likely explainable by non-biological chemistry. The life on Venus moment faded, not because Venus was proved sterile, but because the evidence could not bear the weight of the claim. In 1996, NASA scientists announced they had found fossilized bacteria in a Martian meteorite known as ALH 84001. President Clinton gave a speech on the White House lawn. The announcement was later undermined when further research showed the key evidence, magnetite crystals, could have formed through entirely non-biological processes. The history of astrobiology is a history of moments that felt like discovery and turned out to be something else. This is not a failure of science. It is how science works. The bar for claiming you have found life on another world is, and must be, extraordinarily high. Because once you make that claim, you cannot take it back. It reshapes everything. Put yourself in that position for a moment. You have spent years studying a single planet. You have fought for telescope time, analyzed the data, reanalyzed it, presented it to colleagues who have torn it apart. And now you have a signal. It is not 5 sigma. It may never reach 5 sigma in your lifetime, but it is there, and it looks like life. Do you publish? Do you wait? Do you spend the rest of your career hoping someone else confirms what you already suspect but cannot prove? This is the position every scientist behind every one of these signals is in. The signal exists, the planet is real, the debate is ongoing, and the only thing that will resolve it is more data. So where does this leave us? This is the point where everything changes, not because we have found life, but because we have reached the moment where we can. For the first time in human history, the question of whether we are alone is no longer a matter of philosophy or faith. It is an empirical question. It is being tested, not perfectly, not conclusively, but genuinely with real data from a real telescope pointed at a real planet. K2-18b may not have life. The DMS signal may turn out to be noise or abiotic chemistry or a measurement artifact. The planet itself may be a gas world with no surface and no ocean. The Hessian hypothesis may be wrong. All of those things are possible. Some of them are likely. But K2-18b is not the only planet. It is the first. It is the trailblazer. But the telescope that found it was never built with this as its main job. Webb's founding mission was to look back at the first galaxies, the birth of the earliest stars, deep field cosmology, not chemistry on a single small planet. Exoplanet atmospheres were part of the plan from the start, but a smaller piece of it, and the specific technique being used here, reading a planet's air one transit at a time, has been pushed further than anyone expected, right up against the edge of what the telescope can actually resolve. The fact that we are having this debate at all, the fact that we can detect a single molecule in the air of a world 124 light-years away, is itself extraordinary. The telescopes coming next are different. In 2029, the European Space Agency will launch Ariel, a telescope designed from the ground up to study exoplanet atmospheres. Unlike Webb, which divides its time between hundreds of competing science programs, Ariel will be dedicated entirely to one task: reading the chemical barcodes of 1,000 alien worlds. NASA's Nancy Grace Roman Space Telescope launches this year, August 30th, 2026, carrying a coronagraph built to block out starlight entirely, so planets can eventually be seen directly instead of read through a shadow. And in the 2040s, the Habitable Worlds Observatory will launch, the first telescope optimized to search for biosignatures on Earth-sized planets in their stars' habitable zones. It will study around 25 Earth-like worlds. It will look for oxygen, water, and methane in combinations that cannot be explained without biology. It will take the question we are asking now, is there life on K2-18b, and ask it of dozens of worlds at once. Consider the arc of this. For most of human history, we did not know whether other planets existed at all. The first exoplanet orbiting a sun-like star was confirmed in 1995, 31 years ago. There are people alive today who were born into a universe where we did not know if any other worlds existed. Since then, we have found more than 6,000. We have measured their masses, their radii, their temperatures. We have read the atmospheres of a handful. We have debated biosignatures on one. If the history of exoplanet science were a human lifespan, we would still be in childhood. The discoveries we are debating today, the tentative signals, the contested claims, the 3 sigma uncertainties, will look to the astronomers of 2050 the way the Wright brothers' first flight looks to the pilot of a modern jet. It is not wrong. It is just the beginning. You are sitting here on this planet watching a video about a world you will never visit. The light that carried the DMS signal, if it was DMS, left K2-18b 124 years ago, around the time the Wright brothers were experimenting with gliders on the dunes of Kitty Hawk. It traveled across the void at 300,000 kilometers per second, crossed the emptiness between stars, and struck a mirror floating in space that humans had placed there specifically to catch it. Think about that. A species of apes on a small rocky planet evolved language, then writing, then mathematics, then the physics of light, and then built a telescope so precise that it could detect a single molecule in the atmosphere of a world 1.17 quadrillion kilometers away, by watching the light of a star dim by 1 part in 10,000 as the planet passed in front of it. Whatever you think about the odds of life in the universe, you have to grant that this is extraordinary. This reaching, this straining to know, this is what we are. Carl Sagan was asked once what he would say to an extraterrestrial civilization if we ever made contact. His answer was not about physics or biology or technology. He said, "We are a way for the cosmos to know itself." K2-18b is 124 light-years away. The DMS signal is uncertain. The Hessian hypothesis is contested. But the act of looking, the act of building a machine that can read the air of another world, is itself a kind of answer. Not to the question of whether we are alone, but to the question of who we are. We are the species that looked up, that asked, that built a telescope, pointed it at a faint red star in the constellation Leo, and watched. The data will keep coming, the bar will stay high. And one day, maybe from K2-18b, maybe from another world we have not yet discovered, the signal will cross 5 sigma, and everything changes once again.